Hi, welcome to the sixth inquiry activity, the sixth instructional video in this course. This is actually the first video of part 2 of the course, and we're going to be looking at isotopes. We're going to continue our discussion about atoms, and in particular we're going to be looking at how can an atom of a particular element be slightly different? How can they vary just a little bit? So we're going to be asking this question and answering this question: are all atoms of an element alike? And already you may be thinking, wait a second, I thought you told me that atoms are going to be the particle, the unique, individual, special particle of an element, and for a particular element they're all going to be identical. That is true, but there could be slight differences. While they all have the same chemical properties and they all have the same number of a certain subatomic particle, there are other things that can vary a little bit, and we're going to be looking at that today in our discussion about isotopes. So, glad you're here. Let's dive into our discussion about isotopes. Hopefully you've already finished this inquiry activity. It's always helpful to do the inquiry activity before coming to this instructional video. And as we talk about atoms here today, I want to welcome you to the part 2 of 4, the part 2 section of this course. And this is going to take us through a number of different topics as we look at look deeper into the topics of chemistry. All right. The following activity will help you learn the important structural characteristics of an atom. How do we classify atoms? If you remember from a lecture previously, we talked about classification of matter. Well, now we're going to be looking at classifying atoms. How does the combination of subatomic particles affect the mass and charge of an atom? And what are isotopes? This is just a sampling of what we will address. Throughout this activity, you will want to keep both Model 1 and a periodic table handy. So if you don't have a periodic table out already right now, I suggest that you either pull one up on your computer or get a paper copy and have a periodic table ready to go. All right, let's look at Model 1. I always like to, when I am offered a particular model, I kind of like to just observe it a little bit and make sure I understand everything that is being presented to me before I dive into the questions. So I'm looking up here, and the title is Isotopes of Hydrogen. And down here you notice it says isotopes of carbon. So we're looking at two different elements here. And further on, you'll notice it says isotopes of magnesium. So we have three different elements that we're going to be looking at. Right here, we have symbols. So it looks like H is going to be the symbol for hydrogen, but you'll notice that there's slightly different numbers beside that H. And that is going to be then diagrammed here below. And then there's some blanks down here where we're going to be looking at the number of protons and the number of neutrons. It looks like this symbol right here is going to denote a proton, and this empty circle is going to denote a neutron. And the same thing happens down here for carbon and for magnesium. So let's jump into these questions as we look at isotopes. Question number 1 says, refer to Model 1. What subatomic particles do the following symbols represent in the atomic diagrams? And, as I already mentioned, you have protons are the plus, neutrons are the empty circle, and I failed to mention this one, but there's a little negative sign right there, and that is going to be your electron. So this says electron cloud, and that is going to be a negative symbol. So you've got electrons that have a negative charge, you've got protons that have a positive charge, and you've got neutrons that have no charge. It says complete the table in Model 1 by counting the protons and neutrons in each atomic diagram. Divide the work evenly among group members. If you don't have a group, you can do it individually and you can learn by yourself, and then you can refer obviously back to this video and we can work together on it. So if we are going to count the number of protons and neutrons in each of the diagrams. So we have quickly, we'll look at the number of protons here. We've got 1. Number of neutrons is 0. Here we've got 1 and 1. It's here in the middle of the atom. That's the nucleus there. This is representing the nucleus, and then you have your electrons outside of that nucleus. And again, here we've got inside the nucleus, we've got 1 and 2. I'm just going to make a little comment here. Notice 1, 1, 1 for hydrogen, but 0, 1, and 2 for hydrogen when it comes to the neutrons. Just keep that in mind. For carbon, number of protons. If we count the number of protons here, we've got 6 protons and 6 neutrons. For carbon-13, we've got 6 and 7. And here we've got 6 and 8. Notice it's always 6 protons for carbon, but the number of neutrons can vary. Magnesium. For magnesium 24, let's count the number of protons. If you count all the pluses inside the nucleus there, you're going to come up with 12. And if you count all of the neutrons, you would also have 12. For magnesium 25, it's 12 and 13, and 12 and 14 for magnesium 26. Okay. Find the 3 elements shown in Model 1 on your periodic table. So the 3 elements, as we mentioned already, hydrogen, carbon, and magnesium. And you can locate those on your periodic table if you haven't already. Hydrogen is the symbol H, carbon is the symbol C, magnesium is Mg. What whole number shown in Model 1 for each element is also found in the periodic table for that element? Well, if you look for the whole number, what they mean by that is not a decimal number, just looking for a single value, a whole number, and for us, that whole number is going to be the number of protons. So the number of protons is on the periodic table. You will see each symbol like H in the periodic table, and then you're going to see a 1 somewhere in that box, and that's denoting the number of protons. For carbon, you will see, as you'll notice up here, carbon, you're going to see the number 6 in that box for that particular element. And for magnesium, you're going to see a 12. So look on your periodic table and locate those whole numbers. The whole number in each box of the periodic table is called the atomic number of the element. What does the atomic number of an element represent? The atomic number is representing the number of protons in the nucleus of that element for that, of the nucleus of the atom for that element. So every element has always an atom with the same number of protons. The number of protons never changes for an atom of an element. Always, 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 always. Every hydrogen atom has always 1 proton. Every carbon atom always has 6 protons. Every magnesium atom always has 12. Okay? That's kind of it's like its ID, its identity. So the atomic number is the ID of the element. It is its ID badge. When you see that number, you know it is a particular element. Refer to the isotope symbols in Model 1. Relative to the atomic symbol, H, C, or Mg, where is the atomic number located in the isotope symbol? Here's what they mean. If we look at the isotope symbol, right here, we've got isotopes of hydrogen. There are 3 of them given to us. And it says, refer to the isotope symbol relative to the atomic symbol. Where is the atomic number located? So this is your symbol, H. The atomic number is always going to be lower left. 1, 1, 1. Always. For carbon, here's your symbol. 6 is always going to be your number of protons, and it's going to be located next to the symbol, lower left side of the symbol. For magnesium, it is 12, and it is located in the same location, but it's 12 for magnesium. Okay? So that subscripted number is going to be representing the number of protons for that particular element. Lower left. Refer to your periodic table. You should have one out. How many protons are in all chlorine atoms? So if you look in chlorine, you look in your periodic table, find Cl on your periodic table, and then find that whole number. Find that whole number there. Find the atomic number for chlorine. Okay? Did you find it? So let's find out. Chlorine has how many protons? What's the atomic number of chlorine? In question B, it says, a student says, I think that some chlorine atoms have 16 protons. Explain why this student is not correct. Well, if he says they have 16 protons, 16 is not the atomic number for chlorine. What's the atomic number? 16 is the atomic number for what element? Find it on your periodic table. That actually is for sulfur. It's a completely different element. Okay? So 16 would be the atomic number for sulfur, not for chlorine. So that would not be a chlorine atom. If it's got 16 protons, it's sulfur, always. Always, always, always. Every sulfur atom has 16 protons. Okay? Let's move on here. Number 5 says, refer again to Model 1. In the isotope symbol for each atom, there is a superscript, the raised number, still on the left side of the symbol. This number is also used in the name of the atom, like carbon-12. It is called the mass number. So how is the mass number determined? And why is this number called a mass number? Well, let's look up here. You'll notice that we have 1 proton, 0 neutrons. If you add those together, you're going to get a total of 1, and that is the total mass of that hydrogen isotope. 1 and 1, if you add those together, you get 2. 1 plus 2 gives you 3. And if that, as we're being told, if that is a mass number, it must mean that a proton and a neutron are considered to have equal mass. Okay? So to make up the mass of that particular atom, you are just going to add the number of protons and the number of neutrons. Each of them are given a mass value of 1. It's actually, the unit is called an atomic mass unit. We will talk about that a little bit later as we talk about mass and using moles and mass in order to do look at different atoms and their composition. But in any case, protons and neutrons are going to be added together to give you the mass of that isotope. Just like here, 6 plus 6 is going to give you the mass of that particular isotope. 6 plus 7 is going to give you the mass of that particular isotope. And it is named then using that mass. Carbon-13 is a unique isotope for carbon where you've got 6 protons and 7 neutrons. Carbon-14, 6 protons always for carbon and 8 neutrons. So that gives you a total mass of 14. How is the mass number determined? We just said that we're going to add protons and neutrons to give you the mass. Why is this number called a mass number? Your protons and your neutrons those two have a particular mass. They're going to be equal. The mass of the proton is going to equal the mass of the neutron. Those are the two subatomic particles that make up the mass of your atom. An electron is so tiny that its mass is insignificant compared to the protons and the neutrons. Okay? Alright, number 6. Fill in the table for atom 1 and atom 2. We don't really know what those are. Shown below. We just know that we have a diagram here for atom 1 and atom 2. So the number of protons, we just count the pluses. For atom number 1, there are 5. 1, 2, 3, 4, 5. And there are 6 neutrons. The mass number, therefore, is going to be 11. Just add neutrons and protons together. Atom number 2, you've got 9 and 7 for a total of 16. Back in model number 1, which corner of the isotope symbol contains the mass number? So that would be your upper left corner. So for example, for hydrogen 2, your upper left corner has the mass. The bottom left corner is going to be your atomic number, which is number of protons. This mass is number of protons plus number of neutrons. How is the mass number of an isotope expressed in the name of an atom? It is hyphenated. So you're going to take, for example, hydrogen 1 or hydrogen -2. So those are just hyphenated. Carbon -12, carbon -13. Okay? Number 8, it says write an isotope symbol, similar to those in Model 1, for each of the atoms in question 6. So we go back up here to question 6. Here we have our 2 atoms, and we have written the number of protons and neutrons and the mass. So again, it is the number of protons, that's your atomic number, and the mass, those are the 2 numbers that are going to be in your isotope symbol. So for atom 1, this, by the way, if it has 5, if you look on your periodic table, you'll see that that is boron. Okay? So we put the mass number as your raised value, 11, and your atomic number is the subscript number. So 11 goes here, and 5 goes there. And if you look on your periodic table, what element has an atomic number of 9? Well, that would be fluorine. So it's F. And again, your mass goes here, 16, and the atomic number, the number of protons, goes down there. Write the name of the atom. So this is going to be your boron -11, and this is your fluorine. Fluorine -16. Number 10, fill in the following table. We are given now the symbol of a particular element. There's potassium, there's fluorine, and we are given the numbers. Remember, the top number is the atomic mass, that's protons plus neutrons. The bottom number is the atomic number, that's the number of protons. So we can fill in this whole table just given just given the symbol, or given a couple numbers down here that are going to help us fill in all the other information. So let's do this. The isotope symbol, we're given potassium 40. This is potassium 40, the mass. The atomic number is 19, that's the number of protons. The mass number is 40. The number of protons is 19. And the number of neutrons then is going to be 40 minus 19, which gives us the 21. Same thing here. Atomic number is 9 for fluorine. you've got a mass number of 18. It's given to you right there. Number of protons then is going to be the same as the atomic number. That's 9. And to find the number of neutrons, you take the mass minus the number of protons. Okay? And this one, we've got atomic number of 16. So I know that whatever my symbol is, I'm going to have 16 is going to be my raised number. And if you look on the periodic table, you'll notice that what symbol or what element has an atomic number of 16? Sulfur. Oops, sorry, I put this in the wrong spot. My apologies. Sulfur, my 16 is going to go down here. And if it's 16 and the number of neutrons is 15, those two added together are going to give me my mass of 31. So my mass goes up here, and the number of protons is also the same as the atomic number. Okay, so this would be sulfur 31. All right, number 11, key point. Consider the examples in Model 1. Do all isotopes of an element have the same atomic number? Do all isotopes of an element have the same atomic number? Yes. Yes, I cannot emphasize that enough. Just because it's an isotope doesn't mean you've changed the element. Isotopes of hydrogen are all hydrogen. Isotopes of magnesium are all magnesium because they have the same atomic number. They have the same number of protons. It is the number of protons that gives an element its identity. Give at least one example or counterexample from Model 1 that supports your answer. So, all carbon atoms, for example, have an atomic number of 6. All of them. So I can't emphasize that enough. Every element, the atoms, always are going to have the same number of protons. Different neutrons, that's why they're called isotopes. Isotopes have a different number of neutrons for a particular element. Do all isotopes of an element have the same mass number? No, because they have different number of neutrons, and it is the mass that is determined by the number of protons plus neutrons. Protons never change for an element, but the neutrons can, therefore the mass can as well. Okay? And it says, considering your answers to question 11, write a definition of an isotope using a grammatically correct sentence. All right, I may not use a grammatically correct sentence, but I encourage you to do so. And then you can talk a little bit about this with anybody that you are working with, or just compare to what we have here. Okay? So basically you have an isotope is an atom with same number of protons but varying number of neutrons. Okay? Sorry about that. So, if you have different number of neutrons, that is going to allow you to have isotopes. But that doesn't change the identity of that particular element. Okay? The proton is what determines which element you have, not the number of neutrons. 13, consult the following list of isotope symbols. Here we have lead, bromine, lead, platinum, and again lead, and says which of the atoms represented by these symbols have isotopes of each other. So isotopes here of lead would be the first one, the second one, and the third one. Notice they all have 82, 82, 82, but it is the masses that are different because they have different number of neutrons. Here, these are your isotopes of bromine, bromine. You have 35 and 35 for both of them, but it is the mass that's different. And then this one is by itself. There are no isotopes, no other isotopes listed there anyways for PT. Which of the atoms represented by these symbols are isotopes? Just talked about that. And which part or parts of the isotope symbol was the most helpful in answering part A of this question? All you need to look at is the symbol. The symbols all have to be the same, but the masses have to be different to determine if you have isotopes or not. The symbols and the atomic number will all be the same, but the only thing that's different to determine if you have isotopes is the mass number. Okay? All right, let's wrap this up. Determine the number of electrons in each of the atomic diagrams in Model 1. By the way, this is going to lead us into talking a little bit about how the number of electrons may change. This is for a future discussion when we talk a little bit about charged particles, ions. So the number of electrons in each of the atomic diagrams in Model 1. In a neutral atom, how does the number of electrons compare to the number of protons? Electrons have a negative charge, protons have a positive, so if you want that atom to be neutral, you're going to have the number of electrons equal the number of protons in order for it to balance out, cancel each other out, and be neutral. Discuss why this relationship is important in making a neutral atom. I already just mentioned that. You have to have the same number of negative charges and positive charges in order to cancel each other out. Even though a proton's mass is much bigger than an electron's mass, they have the same magnitude of charge, just opposite. Negative and positive, but the magnitude is the same, so they'll cancel each other out. 15. Refer to the hydrogen isotope in Model 1. Each isotope has a special name derived from Latin: protium, deuterium, or tritium. What structural feature do these names refer to in the atom? Well, the PRO is going to talk about 1, the mass of 1. The prefix DEUT is going to talk about the mass of 2. And then TRI, that's going to tell you you have a mass of 3. So sometimes you'll see unique names for the different isotopes instead of just hydrogen 1. This would be hydrogen 1 instead of just hydrogen 2, hydrogen 3. You might see unique names, but those names do kind of have prefixes that go along with the mass of those isotopes. 16. Can two atoms with the same mass number ever be isotopes of each other? What we mean by that is, can two atoms with the same mass number ever be isotopes of each other? Well, if two atoms have the same mass number, either they're identical, they're the same atom, and therefore they're not going to be isotopes if they have the same, if they're completely identical, or they're atoms with different atomic numbers, but they happen to have the same mass because the protons and neutrons add up to the same value. Okay? But in order to be isotopes must have same atomic number. Protons, remember? So, two atoms that have the same mass number, can they be isotopes of each other? Well, if they have the same mass number and the same atomic number, then they're identical and they're not isotopes. If they have the same mass number but different atomic numbers, then they're not the same element and therefore they cannot be isotopes of each other. Okay? All models have limitations. What they're saying is, in all of these inquiry activities, these models are meant to represent something to help you understand something that you may not be able to see. But there are limitations. We can only take a model so far, let's say. What characteristics of Model 1 are inconsistent with your understanding of what atoms look like? Well, first of all, the proportional size of the electron and the proton and the neutron and the nucleus is probably not correct, okay? So sizes are probably wrong, and those are just drawn so that you can see them, okay? Electrons are so much smaller than a proton and neutron. Obviously, as far as color and stuff like that, we're just putting a plus sign and filling it in with black or making it blank in order to represent something, okay? So our model is just meant to represent something, but it's representing something that you can't see. So we use symbols and colors and diagrams to help you visualize that and better understand it, okay? All right, I hope this is very helpful, and continue to look back at this video if you've got questions. You can certainly review it, and you can pause it at any point in order to help you further understand all these concepts. All right, I'll see you in the next video.